slides? No, you. See?
He doesn't want to download the reference image because.
You don't want to.
Don't we have already those?
Yeah, but I think it's not copied in the images folder.
No, we don't have them.
Because when we were copying quickly all the images, I think that one was missing. So.
Okay, in Texas,
Which one of this is this? I copied this. Yeah? This one.
This. It doesn't.
Yeah, ready. Are you ready there?
No, but you don't have the.
No.
Or whatever. Ah, sorry. Sorry. I don't want to. Maybe I stopped one of your processes. Because title is wrong. Oh. I'm fighting with this. Sorry. That should be okay. Yes. Okay. Okay, it's still uncompressing the data, the calibrated data. Okay. So then we can start with a bit of explanation on what are we going to do today. So today we are going to try to image ourselves one of the science verification data sets with CASA. So we are not going to simulate anymore with AbSynSim. We are going to work with real data. And yeah, you will see the difference, how long it takes to create an image with respect to the simulator. I have put again the basic links here about CASA. I'm not, I tried to make them work, but I'm still not sure if when you copy or if it really, there is a character problem if you really go to the correct website. So I'll try to fix it again. Here there are the general ALMA guides. So you can perhaps go and see there are many, many examples there. We will concentrate in one. We will make spectral line images of one galaxy that you will see later. This is target. You have here, this link here forwards you to the ALMA wiki page for data reduction of this target. Perhaps you can open it. When we tried to open it, the word title was not correctly written in the navigator. So if you want to open that, does it work for you guys? In any case, don't worry too much because I created a website for our exercise today that you will find later. But the general description of the target and all the steps that you have to do to calibrate it are located in that link. I already asked you to start extracting the calibrated data file because we copied it in all the machines, but then we didn't extract it. Sorry about that. And it may take a while because it's a big file. That's the problem of working with ALMA data that is very big. It's extremely big. Are you all extracting the? Excellent. Okay, so in the link to the paper that published the results on the data that we are going to work on today, it's public, it's there. You will also have the link in the website that we are going to use for performing the imaging steps. So it's a strongly lensed galaxy. So you will have we will be imaging the Einstein ring of the galaxy. And here is, just a map on the images results in that paper. So we will be working with one of these lines. I think CO78 is this one here. You will see it better. This is again the way to open CASA in case you don't remember well, you can start opening Casa in your computer. You can go to the folder Casa version blah 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 and execute Casa this way. Have you all opened Casa in your computers? Okay. So then, everything that we are going to do today is under my website in the observatory, in the Sterrebach. So hopefully, you will be directed somewhere that looks like here, like this. Do you get to this website? So this website was prepared by one of my colleagues in the UK, in the UK Alma Notes, Anita Richards. And so I have adapted her website by putting more explanation in the steps and putting some more pictures on what are the outputs of every step for you to be able to follow it. So we are going to use the band 6 data of this galaxy, and we are going to perform imaging of this line, COJ87. Yeah? So I guess Alan may ask you later in the afternoon, what does this mean? Okay, so here I provide the links of where to locate the data in case you were willing to repeat this exercise in the future. Now it should be in your computer, so this part here you can skip it. And here in this band6 imaging.py, that's the original file that they used to produce that image here. Okay, so this is the one that is provided in the ALMA Casa guide. We made, Anita and I also made, after Anita, some modifications on the inputs to the cleaning, basically, to the cleaning task. You can choose many parameters, as you know, so depending on how you want to image, you may want to change some of the parameters, so we did. But here is the same exact input parameters that they used to generate that image there, okay? In case you wanted to reproduce all the steps kind of automatically without opening windows and selecting cleaning regions, you can just go ahead and run this. Normally, when you, as a PI, receive your ALMA data, you download the raw data and you run this script that is provided. So you just have to wait until it's done, and then you have the images already. Now, in our case, we're going to do it step by step. So you understand what's all the steps that are performed in this script and why are they done. Okay, so this line has a risk frequency around 900 gigahertz, but this galaxy, it's located at a redshift of 3. So then you have, a change in the frequency that we will observe in the sky. You can go and, for instance, visit NET. Have you ever used NET to check the properties of this target if you would like to see images in other bands or velocity information, sizes, etc.? So yeah, you can go there and visit NET. The important thing about this is because this line is very weak, so we will need to use some previous information from the target, right? Because it's so weak, if it was very bright, you will already see where is it located when you plot the visibilities. You will see later. But because it's so weak, we don't see it. So we have to make a guess. And using the information of the velocity of this galaxy and estimating how broad the line could be, we are going to make like a window saying, okay, around the center velocity of this galaxy for 800 kilometers per second, we expect the line there. So we are going to avoid those velocities for subtracting the continuum. Okay? This is why some information is required in this case. Okay. Okay, so you can, here you also, again, you have the link to the paper. And also, there is a more recent press release regarding this very same target. So we can, check there. Because not only they detected a galaxy, but a dwarf companion. So you have the press release here, which is from April this year. Okay. You will be using, during this exercise, the calibrated data file that you are uncompressing. And also, just for a guidance, we don't need to work with these images, but just for a guidance, it will be good to check to see the image of the continuum. Okay, this is the only one that we will use from the folder images. The other ones are the ones like this that you are supposed to obtain at the end of this exercise. So in case you fail to make the full image or the full data cube, you can go and check how is this data cube. Okay? Okay, so now the first time when you receive a data set, the first thing you do is just to check what's in there. And for that, we use the task listops, which basically makes a summary of everything that has been done during the observations for this target. If you have already extracted the data file, it's finished? Yes. So then in Casa, you can go and run this command. Assuming in Casa you go to the folder where you have the calibrated data. So you can run listops on this file. If you don't put a list file, the output will be written in your log window. If you specify a list file, the information of the observations will end up in a file if you want to keep it for later use. So this is the output, actually. Okay, it doesn't recognize it as a text file. It's just a text file. It doesn't want to open it. Okay, whatever. I'll go. I don't know if it's opening to you. Okay, so you probably are seeing something like that already when you do list ops. So here it's telling you this data file is a combination of 9 different executions. So every execution is listed here. So there were 9 executions. They were reduced and put them all together in this file. So now here you have all the scans that were done and are here in this file. So every time there was a scan performed on the source, it's written here, the duration of the scan. So as you can see, there are many, many scans for each one of the observations. So this is observation 4. This file is the output of extracting only the science target from the full observations. Because what we do when we observe with ALMA is to observe a flux calibrator. It can be a planet, for instance, that we use to calibrate the amplitudes. And then what we do is because there are not so many bright sources in the sky, the bright sources are the ones that we use to calibrate the amplitudes. And then nearby our target of interest, we look for a small for a bright source to calibrate the phases. So the strategy to observe with ALMA is just go and observe for a while the flux calibrator. Then, like a planet like Jupiter or something like that, then you go to the target field. You observe for a bit the phase calibrator and your target. Phase calibrator and target. This is what you do. So then, when you have your data, you calculate the amplitude scale of your flux calibrator, and you transfer those solutions to your target field. And then you look for the phase calibration of that phase calibrator, like the phase solutions for the calibrator, and you transfer that to your target. After all this process, that we will look into it tomorrow, after all this process, the data is calibrated. And here, what they have done is just split out the data for the target. We don't have the data for Jupiter or the phase calibrator. We only have the target here. The original data set is much more big, and you could also download it if you are interested in. But here that's why it only appears SDP 81 in the list ops. If you were looking into the list observations of the full data set, you will see all the different, how the ALMA, the schedule was performed, like calibrator, target calibrator, all the time. Okay. And these, finally, are all the antennas that participated in the observations. Okay? So a better way to visualize which antennas participated in the observation is use the task plot ants. This is to plot the antennas. So if you go and plot the antennas for your observation, does it work well to copy paste? Okay. Okay, so here you have this is what you were used to see. You cannot?
I get the same.
Ah. Okay.
Sí. Era como por la ubicación del archivo.
No estaréis, where are you?
Where are you in the casa?
No, you need to go, sorry, you need to go to the calibrated calibrated data.
We only have the folder reference image.
No, but in calibrated data there, yeah?
Did you put a link?
And yeah, and there, also in that, inside that, yeah, sorry, in the, yes, if you run it there, yeah, sorry, all these CASA tasks need to be performed in the same folder where you have the file C007 inside calibrated data folder. Okay? Otherwise, you will need to provide here the path to the file. No, but this is, where are you? Sorry. This is the one that you need to extract. Okay, sorry. Extract aquí. Sounds good. Sorry, it will take a bit, but you will get it. Perhaps, yeah, I didn't point it you well. But you can, yeah, you can open Casa. Have you opened Casa?
Yes.
So perhaps you can go to the, if you want, meanwhile it gets extracted, you can go to the imaging folder. Yes. Excellent. It's okay, it takes a while because it needs to open all the log and everything. Have you plotted the antennas? No? So yeah, you can now compare what you have already learned from AppSimSim. So you can see what's the distribution of antennas that you had. These observations were done in the early days of ALMA. So you can see that there are not so many, like, it's not like the ideal spatial spiral distribution. I think you can do zoom in, perhaps? No, but... okay. Yeah, I could... yeah, but I thought you could do like something more with the mouse. Do you think this like...
Yeah.
No, but this is just the location in the...
If you change...
It's just to change. No. I think you should be able to... This is to center? Now. It's like with the... pressing the...
right.
yeah. Okay. I'm pressing the right and sliding, so you can see all the antennas that... right? What? Is it still...
El problema es...
okay. Yeah, so it takes a while because it's averaging all this data. It's making an average to display. So it takes a while. Yeah, it's a huge data set. So if you try to do a plot MS without averaging at all, you may get an error saying Casa has not enough time space to load it. That's why we are making time average and channel average, because otherwise the resources of the computer are usually not enough to display all the data. So, and yeah, we put here a very big time range to average, so we average all of it. You could... oh yeah, so have you plotted the antennas? You can make a zoom with the right click, with the right button of the mouse, I think. I think you have to like, select here and then something, something like that. It's not very user-friendly, but I don't know how I'm making it. Now. So this kind of, if you click into the crosses, the arrows in a shape of a cross, then with the right, it's like
a circle.
yeah. Okay. Yeah, if you go and you click here, you can then with the right hand. Oh, okay. So I kind of I think whatever. Yes, like a circle, and you can expand it and see. How close? Yeah, it's not very.
How do we plot the
Yes.
antennas?
So you are checking the final cube. You are checking the images now because you are still extracting. It's okay, no worry, because you can do something else meanwhile, right? So this is the data cube that we are going to obtain at the end, hopefully. And you can, for instance, you can play and see what happens. You have many channels, so at some point you should be seeing something appearing there. Are you seeing this green? Perhaps we can stop and change the color scale for something more contrast, you know? Perhaps something like this. And then we can try to play it again. You see?
This has
That
to
was
do
the-
with the velocity of the, no?
Yeah, this is the galaxy appearing at its own velocity. So because it's lensed, if it was not lensed, you would see like a normal galaxy as we saw appearing in the channel maps. But because it's lensed, it appears in a ring. So this is what we are going to image. And you can also, what you can do, this is what we will be using when we clean, so perhaps you can then also explain to your colleagues, is to overplot the continuum. The continuum is an average of the whole band. So then you can do a contour map, and in principle, oh, but it has a different.
Aspect ratio, no?
Yeah, it should take into account the shouldn't happen. This shouldn't happen. Should be using the coordinates accordingly. It's a bit weird. I think I don't know why it's not.
They are supposed to be in the same UV plane, no?
Yeah, they are supposed to be one on top of each other. So this should appear here, but I wonder, because the beam perhaps is wrong. I think the beam is wrong in this image. That could be, I don't know, because it should be appearing on top. So I don't know why it's. It's very weird. Anyway, if it's already extracted, almost. Okay, so when it's extracted, you go in Casa, you do CD, blah blah blah, to go to this folder. Yes, and do these stops if you want, or if you don't want, you can already get the file there, this one, and you can do the plot antennas. So are you doing the next step, which is to plot? So plot MS, it's used to inspect the visibilities. So this is before imaging. That is when you are inspecting the Fourier transform of your dirty image. Okay, so that's why you are choosing displaying the amplitudes or the phases, and in the x-axis you can put channels, you can put scan, you can put UV distance that we will use later. So all the parameters that we were using to inspect the Fourier transform space in AppSimSim, you can use them there to plot the real data. So in theory, if it was a point source and you were plotting with plotMS the amplitudes and UV dist, you would see that you will get like a constant value for the amplitudes. It's clearly not a point source here, you will not see that. And then if you were plotting the phases, you will get a zero phase, a mean zero phase. But here, what we usually do is to use PlotMS to do a quick inspect to see whether we can see a signal already, to see in which channels the line is. And then we can use those channels for imaging. But here, we clearly don't see any spike. So we will have to guess where the galaxy is when we image. Another thing that can happen here is that we might see a spike, but actually it's not coming from the target itself, but it's coming from a water vapor line that just happens at that frequency. Because there are some frequencies at which we don't get good transmission, and then what happens here is we see spikes that are not related to the target. So what we need to do is go to and check the ALMA coverage and see whether there are any water vapor lines there. And if that's the case, then it's not coming from the target, and we have to discard that data. Okay, so this is a very kind of well-behaved data set, but still, the people that have been working with it realize there are some problematic points that can be flagged. If you flag discrepant data points in your UV plane, then it's it improves errors later in the image. Hopefully, we will be able to see some examples of what are the implications of an error in amplitude, what happens in the image if you don't flag those points. So if you do PlotMS with respect to scan, then you can see that there are these nasty points here that make like very high amplitudes that should be like taken away. This is just a bad response of a certain baseline. So what you can do in order to flag these points, first of all, you would like to make a backup of your original flag table. This is very important because if you make a mess by flagging points, then you will not recover what the observatory did. So you can start flagging points, or by accident, by clicking wrongly with your mouse. It's good if you have a backup of your flags. Otherwise, you have to download your data again or whatever. Okay, so if you see it, if you have the PlotMS open, you can always go and select a region with this green plus thingy. You go to the window and select a region. Oh, here I cannot make it. To select those points that you are interested in. And then you go to you press here, and this means locate. This will print in your log window, or perhaps in your terminal. No, in your log, I think. What are exactly those points? So if you do that in your case, it will tell you which antennas and at which time are responsible for this bad response. And then you can take a decision whether flagging the whole antenna for all the time, because if the antenna is giving trouble all the time, perhaps you want to take it out, or perhaps you want to take just one baseline all the time because it's like giving a lot of noise. In this case, there are just two particular baselines that are bad for 2 scans. It's kind of okay. You can easily flag them manually. If you select the region and then press the red flag, then you will flag those points, and they will be taken out from your data set. They will not be used for further processing. Okay? Yeah?
How does the tracking affect the final result? I mean, you are taking out information.
Yes, you are taking out information.
It has to be an impact
Yes.
at the end.
Yeah.
The image.
If you, for instance, are flagging, let's say, the longest baselines, which is a problem that you used to have with these very extended configurations, sometimes it's very difficult to calibrate the longest baselines and they are not giving good response. if you flag them, your resolution will be not as good as you would like to, right? Because your resolution comes determined by the longest baseline. So if you flag the outer antennas because they are just too bad, then your final image cannot have the resolution that you were willing to obtain, to achieve. If you don't flag these problematic data points, you will see like spikes in amplitude will create interference in your image. You want to get rid of this because then you will have like a pattern there, ripples, just because you have a couple of antennas that are performing widely. You take them out and, okay, you may lose one baseline of how many baselines you have. That's okay.
And if I remove not too much information,
Should be.
also will be noted if I'm using?
Well, depends on which information. For instance, you have many scans here, right? You could get rid of one of them if it's very noisy. We will see later that one of the scans in the flagging commands that the people, after flagging these 4 funny points, they saw that the scan 168, that one here, was also kind of funny. You can take it out. Of course, if the data there is not good, is good, this is making the more time you observe, the lower the noise you will get in your final image, right? But if that scan is very bad, you just take it out. And then, okay, you have less observing time, but if it's better behaved, your output will be much better. Okay? I don't know if you managed to open the plot.ms or if it's taking too long to do the flagging. So you can do, as I said, you can flag data points as you wish, at your will. This is a test, so you can try and flag whatever you want. Then you will see what comes out in the final image. But here you can flag from the command line. See, 163 was bad, so they decided to flag it all, take it out from the data set. And then you will see, when you locate these points, if you locate these points, have you done that already? No. When you locate these points, you will see they correspond to the baseline in between these antennas and these antennas, so they flag them. Where are you guys now? Are you in the plot.ms? Okay. Yeah, I thought it would be. Okay. Yeah, I know it's a bit like kind of boring, but extract it.
It's been like this for
Stall.
10 minutes. And when we press compose like passing the extraction, then we open Casa
And it doesn't work, of course.
Yeah. And I extracted all the files and it still doesn't work. And
What is the size of your of this? Are you like what is the size of like the folder? Or? Okay, because maybe it was not properly copied when we did the massive copy in all the. Sorry, you're doing Casa, right? So, in order to, this is a thing to know. In order to run usual terminal commands in Casa, you can write them as usual, but you put and this way you can use all the Linux, CD, whatever. It's not this, but this. No, sorry. Instead of the dollar, is the. So it's 7.4 gigas. You finish the extraction?
yeah. At least
Yeah, okay. Can you guys tell me what is the size of your calibrated data set? Because perhaps that one is corrupted. Yes, calibrated data? No, only the CO07. Another one. No, this inside this? This one. No, 7,9. It's 7.9 gigas, not 7.4.
But I tried extracting it again,
And it doesn't work. So I think
the copy was wrong.
How does CASA or ALMA or whatever defines the antenna zero? I mean, the origin of coordinates are given.
yeah. So
How do you decide?
no, I mean one thing is to plot them in the UV. But this is, remember, this is plotting baseline distance. Okay? So it's baseline distance. So no matter.
Are not the position of antennas.
It's related to, but it's not the position in the. It's baseline distance. So that could be whatever the array is. Yeah, what we do, which is true, is in order to calibrate, we select a reference antenna. Okay, because you are calibrating the baselines. So you do is you select an antenna that is located kind of in the center of the array. And when you check its performance during the observation, it's its response is kind of smooth and flat. And that is the reference antenna you will use to calibrate the rest. Because you are working with baselines, you select one good antenna. But yeah, here it's not that you are choosing in location.
It's not like the position of antennas.
It's baseline distance. Oh, you made it.
Yes, but what I did was in the access, I changed this to scan.
Yes.
And in data, I put scan also.
Yeah.
I don't know if that's good or what.
Yeah, you are, because you are not getting.
Those points you showed us.
Because you are averaging per time and per scan. So I think that's why perhaps you are missing those crazy points.
So I should check this and do again the plot.
Now you can press here and plot. Sorry, it will take a while. But that's because, that's the thing, if you average too much, you may lose some of the spikes, but you have to take a decision. Tell me.
This was my result. I don't know. It seems different, or it's just this.
But you have 600. Okay, 600 scans. Yeah, it's full because we average channels as well, perhaps.
Oh, okay.
Am I averaging channels as well? Yes, so you have to average channels as well. And you can do press here and plot. Yeah. So yeah, you can see that it's a pain to work with ALMA data. It's very big, but if you want to learn to image it, then that's how it works. Tell me.
These lines is the same if I
Yeah, if
Flag
you, yeah, for
this
instance, if you select this, sorry, first you have to do this, and then you select. First what you do is basically locate and see who are responsible of this bad data. If you do locate, then you go to the logger, and it's telling you in which scans which data is bad. So it's telling you the baseline of DA49 with PM04 is responsible at this time of this particular, in scan 307, it's giving you all these problems. So that's the reason. And then when you see that basically come from all the time from the same baseline, here, so you have all the time DA49, PM04 all the time. So that's why they decided to flag this data in that region between the 200 and 400 scans. These two baselines are flagged, okay? And then they also noticed these two pairs, which are basically, once you flag these ones here, then you flag, I think they flagged, oh sorry, upload MS. After that, now I do delete region, so I'm not doing anything. If you wanted to flag, you do like this and like this. Then you can also unflag. If you select, yeah, whatever. But this is the way you could flag interactively, or you can go. It doesn't harm if you flag here interactively and then you also run the command. It's going to reflag or overflag or whatever. So once you flag a region, then you can reload. So then it rescales, and you can see more detail. You will see it. But then you can also delete this region and say, okay, who are responsible for this? I locate this. I go to the log. And then it's telling me 65 with PM04. So these are like too high amplitudes. This is bad. So then that's why in the here they decided to also flag 65 with this antenna. Okay. Hopefully you will have time. You can also go and locate these. And this is scan 163, I think. So if you go to the log. So now here you start seeing that the antennas are like, it's not like something clear. So what's going on? What do they have in common? Okay, they are all in scan 163. So that's why they chose to flag these three.
Okay.
Yeah.
Thank you for
Yes. Excellent.
But here says averaging all channels and all times within a scan.
Yeah. It's okay. Don't worry. You could do channel 128. There are 128 channels. Sorry, I didn't. Yeah, it was in the list of.
This or,
Yeah.
or with this? Because
I think you
here
don't.
it
Yeah.
says within a scan. So you know.
You can. Yeah, I think you can select that, and then you will end up with the same plot as I had. But you can put it or not. Yeah.
Wait actually.
Yeah, but you can see already this spike here. If you go and add a region, select this, and then locate, you go to the log message, and then you will see who are these data points, what do they correspond to. So it makes you a list of which baselines are, at which scan time, and everything. So then you can detect where do they come from? If you are plotting scan, this one corresponds to scan 163. That's why in the flagging command, they selected to flag all these. Okay? And then when you go and you replot it, you will see, well, you have some funny points here. They correspond to these two baselines that we were talking about, and that's why they flag them. So when you can, if you use this window to create a region and then locate, you could do also, if you don't want to flag from the command line, you can use this red flag to flag the selected points manually. They will be flagged. So it's another way. If you just want to one data point or two data points or something more general, kind of, then you use the red flag. If it's something, if you have a big data and you know that the whole scan is bad, then you use the command line to say, okay, all scan 163 goes. If you want to use, like, let's say we want to flag these points here. We just make a region and we flag, and that's it. If you want to, like, flag a whole baseline for all the time, then you use the command line.
Okay.
Yeah. Yes. Yeah, I think these guys, you cannot work, actually.
No. But it already extracted everything.
So,
No, but finish there.
okay, because I think it was because of the copy that we sent around. Perhaps it was not properly done in your computer. So maybe, I don't know, you can go and sit with somebody else.
Yeah. It's okay.
I'm sorry that it's missing half a gigabyte, so no way they can.
Okay, I have several questions.
Yes, tell me.
First, why one to the?
Yeah,
to
it's
the-
just a random number
Okay.
that I have put in there to average the whole time.
So okay. How long is the observation?
I don't know in total.
I can get that information, or okay, you say okay. I don't know. I put it.
I put like
So
a large
so
number, so
okay.
if you wanted to average every minute, you put 60 seconds. But I want to get just a single point for all the time.
That the reason.
So that's
because
why,
that
yeah.
number is like hilarious.
Yeah, you can put to the 11th or to the 20th or whatever. The observation, if
It's
it's
a kind
like
of
2
infinitum,
hours,
same.
yes, it's an infinitum. Yeah, sorry, yeah. It's an infinitum. Yeah, I think I have put a link here, but you guys don't want to lose time with averaging data in PlotMS. Anyway, so yeah, if you want to average, like, let's say you want to do an average for the first half of the observation and then the second half, you will take a look on how long the observation lasts. Perhaps it's like 2 hours, I don't know. Then you can put 3,000 seconds there, and you would get.
Okay. So that's the first thing you have to do, like always, like plot the.
Yeah,
all
you
the
always plot.
observation with
You always plot the amplitude versus time, so versus scan versus channel versus UV distance. You do that in order to detect the baselines that are not performing well, and you want to take them out.
What is a scan? What is
Scan is the individual observations.
So I'm plotting like an antenna. This is an antenna.
No. If you go to list ops, what is? It's a.
Is it
Yeah,
here?
okay. In
Edit.
the here. Okay.
This is the result.
Every of these ones is a scan. So it's just 1 minute observation.
Okay.
But then you have the different days. So you have like the first day starts in scan 8 because the first scans were for the calibrator. And then 8, 9, 11, the 10th was probably the phase calibrator or something like that. 13, so all these are scans of the target. And this number is what you are plotting in the Casa PlotMS, which is telling you the time.
This is a log. This is a log of
This
the
is the log
observation time.
of the observation, yeah. So here in the log, it tells you all the data sets that have been combined, in this case 9.
Okay.
Then, for how long, like this was like 1 minute and a half or something, 1 minute 15 seconds.
I get you.
So this is during that day, on October 12, 2014. And this was, this short observation, this is the intent. So this first short scan was done in order to calibrate the atmosphere. We are correcting for the water vapor all the time. So this scan was done for that.
But it
And then-
also appears here? No.
No, because I think they have been extracted
Because
as...
there's not information of
yeah.
that we care.
Yeah. And then, okay, so this for the first day, then second day, then third day, until you have all of them.
I get you.
Okay, so everything is in here. Now here you have the important information that I forgot to tell everybody. I will go back. The important information that we have to get from here is the setup of the frequency. We will see it later because we want to image, right? But
That's the 100.
yes, 128 channels. The one that, here it's only extracted the CO line in the channels, but you had, I think, 4 or continuum, and you have 2 lines and 2 continuums. So the 2 lines were observed at 128 channel resolution, but the continuum is just one single channel.
Okay.
So here you can see which ALMA band you are working on, and then the number of channels, and the channel width, and the frequency of channel 0.
What do people of ALMA give you? They give you like a single file with different bands, or
It can happen that you have observations that are the first scan observed in band 3, and then the second scan in band 6, band 3, band 6, band 3, band 6. So then you can get, or sometimes they concatenate, you can concatenate them together. You have the band 3 observation, and then you have the band 7 observation. You concatenate them together.
so it depends.
It depends, but it will appear here. Whatever you have done to your spectral setup should appear here.
So this is the main information.
Yeah, that you need to use for imaging. So because the rest frequency is at 900 gigahertz, but this galaxy is at redshift of 3, the sky frequency at which we will observe this line is at 200 something gigahertz. That's why your first channel starts there.
Okay, and then that's
And then those are the antennas that are participating in the observation.
nice. And the names.
Yes.
The names of the antennas.
And that's it.
The 0 is like in the very center of the ray, or doesn't have to.
The 0, which 0?
The zero antenna. I mean.
No, it doesn't necessarily mean that it's one of the
Doesn't mean
central.
nothing.
No,
Oh, okay.
I think I'm not sure if they are ordered by coordinate from the east to the west. Or I don't know the order of the. Here you have this diameter.
This is the what plot and
Yeah.
Okay.
So the A41
Okay.
must be 64, 60, 65, 40, 41. Yeah. 41, 43, 45. So you
I
have
get you. Awesome. Awesome. Okay. Nice.
So and here you really have the location.
That's the location of the antenna. That's the baseline.
Yes. So I think that perhaps you can put this in Google Maps, and then you can see where are they. I don't know. Yeah, and then so here now you have it, the plot MS. So let's say, yeah. So you can select that region and then say locate.
Why can I say that those are body data? Because it's out of the main.
Yeah. So, okay, if it was like we know it's not a point source, right? But more or less all the amplitudes should be
in the same
in the same level. Yeah. You see that for different days you have kind of different base level,
Okay,
but
behaviors.
that's weighted. That can be weighted. But these data points are clearly out of sync with respect to the same points in that day. So there was something going on in those baselines. They were just too noisy.
For sure, there are like several standard deviations
Yes.
away from the mean.
And the same happens with this spike here. So if you select a region and then you do locate,
Okay.
and then you go to the log, it's going to tell you the
If you
responsible
want to
points. So here you can see all these points that you selected are scan 409. This is the field that we are observing. The time, the baseline, the spectral window, which it's on the channel, the frequency, and then the x-axis, blah, 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 and the y point. So they are 0, 14, and this is the scan number.
What do we have to observe? Like, what is the main?
Like here, if I'm looking, these
Okay.
points, where do they come from? Well, they all have in common that it's the same baseline. It's baseline in between 49, DA49, and PM04. All these points,
Are from the same baseline.
yes, this baseline is noisy, it's very bad. You want to flag it. If I select, if I go and delete this region, I go and select this region here, okay, and I locate.
It's going to be like a lot.
You have like here like different baselines, different. You don't. There's nothing in common for us. They're just all these points.
What is the? So this is like the
8 and 19. If
so
you go to
this
the log,
this means is the baseline between the 8 and 19 and 10.
yeah. If you go to the list stops, you have one number before every antenna. So these are antenna 8 and antenna 18. But if I go back here and I just select those points here, okay. Now they all have in common that it's this baseline, the noisy one. So if I go and check what do they have in common, they all of them share that they are this baseline. So I can flag this baseline.
But for that particular time or always?
You can flag it for like this region here.
I know it's already averaged by
that's-
time. Okay. No,
Yeah.
Okay.
It's it's averaged by time. So every scan is averaged by time. Yeah.
So if
But you
I-
can check. You can flag it from scan 300 to scan 500 or something like that.
I get you.
You in the what is the website here? This is the reason of this. So these antennas, they chose to flag them in these scans. Those are the points that we are seeing now. And this other baseline has been flagged in these scans here. Okay. And if we go here, okay, what's happening here? It's clearly one scan is crazy.
It's like a one spike.
Yeah, which scan is this? I don't know because I can't tell. I want to flag this one particularly. So I can go and locate it again. Locate, and then I will see. Okay, now you have like many baselines. You cannot flag one single baseline in this case. What do they have in common? They all have the same scan number.
Where is the scan number?
The X. The X is the coordinate X in plot MS, and the Y, the X and the Y. So they are points that are at
I understand.
around 0.05-ish, 6, and I scan. I want to know which scan is this. So in the log, I see here they are scan 163, and they have amplitudes. Yeah, so I can flag the whole scan. It's much easier to do it from the command line to scan a whole scan than selecting it here, because then I cannot go all the way down. If I try to select that all the way, I might be selecting something else, right? So you do it from the command line. But if you want to like flag all these points here, you can use the red flag, and they will be flagged.
Which one is better? It's better by command line. or to
No,
combine
you,
both?
you need to combine both. If there is something that is really wrong for a long time, for all the time, then it's better to use the command line because then you can flag completely. But if it's just like random points here and there, you can use it's much easier to select certain points from the, with your click, with your mouse, with your intelligence. Imagine that these were like different baselines instead of just one. Then it's kind of difficult to put it in the, how do I select these points? Yeah. Or if it's just a single point that is crazy there, you select it and then you flag with the red flag.
Okay, but first I have to make a backup, yeah? Oh.
Yeah, if you should, yeah, for your good own
Where is the
interest.
backup?
This one,
Ah, okay.
save, mode save.
Okay.
So you first run this and then it will make
Backup.
a flag table copy in that folder that you can restore in case if you go too much and by accident you flag something, or if you flag too much and then you go and say, okay, maybe I was too strict, but yeah, then you can recover. It's more for in case you make something really, really nasty. Imagine, so here I flagged those points, and then I reload it again, just in reloads and plot, and then see all my scales got, now I'm at this level. So I took away the wrong points.
Okay.
Yeah, this is kind of okay now. Yeah, it's much better. So if you flag this and then you reload, then the plot will be rescaled. It's just that. Yeah. Okay. So it's 11 already?
10 to the...
Oops. Okay, I think I think you guys we will. How are you doing? Are you with the plot MS, everything? I think you should launch the continuum subtraction. Otherwise, it will take forever after the break. How are you doing, guys?
It's working now.
So you are connecting to his computer and flagging all his data. Okay, I am. At least it's good that you managed to. So did you manage to do some plots?
We're doing it.
Okay.
I have a question. What is channel?
Yes, this is something I wanted to mention. It's very important. I forgot to mention it when we were talking about the log. The basic information that you can extract from the observing log. So in the observing log, you have every single scan that has been done, the duration, the antennas that have been used. But also you have the setup, your spectral setup. So in this case, we were observing 128 channels, okay? And the frequency of the first channel is 228 gigahertz, okay? This is our channel width. So every channel will have this frequency width. And this is the information that we will be using to estimate in which channel will be the line according to the velocity of the target. So this data set in particular has 128 channels. But it was also 15 megahertz. Yes.
It decreases. So
Well, because, yeah, if you have...
as long as the channel increases, the frequency decreases.
yes. We have this...
So
this
it is weighted.
it have put it in this way, because then when you transform into velocity, then it gets positive, basically. And yeah, so here, that's why we have 128 channels. If the line was strong enough, perhaps we can have time to take a look to TW Hydra or some other strong source, you will already see that the amplitudes of these points are higher. Because this is basically, this will be the continuum, and then you will have like some peaks here, but this line is so weak that we don't see it clearly. What we could also see is like some certain peaks here, and that could be because there is just a water vapor line there we have to discard. In this case, we don't have to worry about this, but this is something that can happen in other observations. So yeah, because this is not, the signal is not clear, we will estimate more or less in which channel is the central frequency of our galaxy. And then we will estimate how many channels will it occupy for the 800 kilometers per second that we think it's wide. And then we will estimate the continuum from just the side channels. And we will subtract that. So that's a continuum subtraction step. But before that, you can do some extra flagging, which is what we were talking about. You had another question from this plot?
And what happens if we get a strong emission from these spaces?
From the
separation lines between. What happens if we have a peak in something between the channels?
Oh yeah, well, because you have discretized it. It's kind of spread, so it goes into half and half, perhaps. That's why you want to, let's say, if you are observing a target which has like a line width of 20 kilometers per second only, you want to make channels so not all the information falls into a single channel, because then you cannot do, right? You cannot see the different velocities. Yeah. So in this case, so it gets discretized. So it goes, yeah. Yeah. You need to, that's why they chose 128 channels, because that will correspond to a velocity of blah, blah, how many kilometers per second in the target. But yeah, if you had like a signal in between, and what you mean, it will get like in both. Yeah. Okay, so perhaps because we are a bit late, you can run the flagging commands already.
All at the same time?
Yeah, you can copy paste all of them at the same. Yes, because otherwise it's 11, and you will not make it to the to the end. And then
So what happened then?
Yes. He's making a backup. Yeah, okay, because you are flagging already, you will not see the spikes, but you are also flagging. Okay. So everything will look smooth in your case. So basically, if you go here to the, so instead of plotting channel per amplitude versus channel, you can plot, in this case, amplitude versus scan.
And what's scan?
Scan is every single observation that has been done on the target. So if you go to the list ops output, have you done the list ops?
Yep. Wait.
Yeah, in the list ops, you have the full information of it's the observing log. Yes, the list ops, yeah. Excellent. This is where all the information, it's the observing log of your data set. So here, there were 9 executions done by Violette. she's an astronomer at JIO. There were 9 executions all combined in one single data set. This is the one that you are working on. So for observation 0, so in the original data set, there were also the calibrators in. There was like the amplitude calibrator, the phase calibrator, the target, observed like subsequently. And here we only took out the target and only the CO data, okay? Because they also observe the continuum. That's why it's not. You will see it's not here. It's only the line data. But in the first observation, they started in the 12th of October, blah, blah, blah. And for 1 minute and 15 seconds, they observed the target. Okay. So this is scan number 9. Then they went to probably the phase calibrator, and then they went back to the target, scan 11, for 1 minute and again something. Yep. Then again, and again, and again, and again. So this is for the first day. second day, 12th of October, blah, blah, blah. They observe again for 2 minutes, then back, another. So in total, you have like, what, 500 scans or something like that? This is what you are plotting when you're plotting scan versus amplitude. So there you can see the amplitude of every time slot that you made. Because sometimes there is just one bad response for a certain short time, and then you can just take it out. And this is what happens why they are flagging scan 163, because when you make the plot of amplitude versus scan, those guys are crazy. So you just take it out. You have 500 scans, so you take one that can make a lot of noise in your final image, so some ripples, so you take it out. So that's a scan. And then you also here have the spectral information. So it was observed in band 6. This is one of the 4 basebands. The other 2 were another line, HO2, and then 2 continuums. So here we only extracted the corresponding, the one that corresponded to the CO. Right? 128 channels and this frequency. This is the list of the targets that are in the data set. This is the only one that you have. And this is the name of all the antennas that participated in the observations that are there in the plot ants that you had. And that's it. So what we are doing, yeah?
That's the width of the antenna.
Yeah, that's the dish size. Because if you were combining the ACA with the 12 meter, then you will have 7 meter antennas here. Yeah, that's the size of the, and this is the location of the exact location of the antennas. Okay, so now you have flagged all this data already. So when if you make this plot, you will not see those outliers.
When you make this what?
If you make this plot after flagging, you will not see the outliers. Okay. It's
At the next command?
Is the flagging already performed, or it's just doing?
It's not ready yet.
You were missing the last one. If you press intro to the last one, yeah. And you have finished? So you can come here in the plot MS and then choose access. You can select, instead of channel, you can select scan. Yeah, if you press S, it will go to the, you can even do scan. Yeah. Because there are so many. And then you can go to, data. You can scan, you can average all the channels that we have, 128, right? And I have put here like a crazy amount of time, so all the time is average. If you wanted to average every 60 seconds, then you put 60 here, but I want to average all of it. If you don't make any average, the data is so big that the computer will complain that it cannot be displayed. So, yeah, and you can plot. And you can press reload and plot. So then in this case, because we have already performed the flagging, you will not see the discrepant points. I'm sorry, guys, because otherwise we will not.
It's okay.
It's 11.
It's okay.
Shall we launch the continuum subtraction? Go to the continuum subtraction, and at least you can start this command, and I will explain. Yeah. You too as well? Guys, have you started the continuum subtraction? Okay, at least if it's running, we can, because you see it's going 0%, 100%. Okay, we take a break, and then we. Is that okay? No break? You can stay here. I'm going to take a break at least 10 minutes. Do you have any questions? Guys, so the continuum crash for everybody, continuum subtraction. Okay, I suspect perhaps it's a memory problem from the computer. because this is not normal. We have two options I'm thinking about. And after we take the decision, we will try to correct for the test. But option number one is that you copy the continuum that I subtracted in my hard disk that I have there. It's a matter of copying this 7 gigabyte data in your computer. That's option one. You mentioned that it's not so, it doesn't take so long, perhaps. Second option, for the more adventurous ones, is that we try to image, let's hope it doesn't crash. We try to image without subtracting the continuum, and then we subtract the continuum afterwards from the image plane. There are always two options to subtract the continuum. The people that use the most is the subtracting before imaging from the UV plane. But you can also subtract the continuum from the image plane. After you have done your image, you basically make an average image of the continuum and subtract it. That's also an option. So if you want, you can keep going with the next steps without the continuum subtraction, just image. In principle, this continuum is not so strong either. But so when you image, perhaps you don't see a clear line rotating in the different channel maps. You will see the continuum all the time, which makes things easier for cleaning, because you will see more clearly the ring, and you can select much more easily the regions you want to clean. So you tell me what you prefer. You can keep going with the imaging to see if it crashes or not, with no continuum subtraction, and then do you want to try? Anyway, for the rest, if I can just take the hard disk around in case you want to copy the continuum subtracted one. Okay? So in which step are you? You all tried to subtract the continuum and it failed? Okay. You all flagged?
Yeah, I don't know if it's already flagged. Before it crashes, it saves the flag.
But you finished these 4 steps?
Before it
and then, then the file should be okay. Because when it makes the continuum subtraction, it creates a new one, which is called .consup. And that's the one that failed, and it's like less than 1 megabyte size. Okay, in any case, you can also try to do. So there is a brief bit of an explanation, something it's important that it's explained there with not very successful typography, perhaps, is that is the definition of velocity that we use in radio. There is a bit of an explanation of the optical velocity with respect to the radio velocity convention. So you guys know okay. So when they define the redshift, they define it this way. But so it's basically a comparison in the wavelength. So in this way, you get when you discretize in channels, for instance, you would get when you bin in lambdas, the corresponding optical velocity would have equal size in velocity. But because in radio we work with frequencies, we want that a channel which has a frequency width of 15 megahertz you have here, when you transform into velocity, you want that also corresponds to equal size in velocity, because otherwise the velocity width of every channel changes with frequency. So that's why we have the definition of radio velocity. It's instead of being lambda minus the reference lambda over lambda 0, in radio velocity we define it comparing the frequencies. And this way, when you transform from frequencies to velocities, every channel, if you have 128 channels, right? In frequency, when you transform to velocity, you want, for your understanding, that they also correspond to an equal width in velocity. So that makes that the optical definition of velocity is not the same as the radio velocity of definition. And when they provide you information on the central velocity of a target, you should figure out whether it's radio or optical definition. It's a bit annoying, but this way is more useful for radio astronomers, but the IAU has deprecated this definition. So at some point, radio astronomers will also have to use the optical definition. And that's why when you submit an ALMA proposal and everything, you can choose if you want to use the optical definition instead. So we will need to move on, but for calculating, in this case, it's convenient because when you want to calculate, knowing the redshift of a galaxy and knowing the line width that you expect, you want to know in which channel it's going to fall. So if you have this information in velocity, you want to transform it into frequency, and you do this back and forth. It's convenient if you use the radio definition, because then every channel has the same velocity width. After all, we are used to think, okay, every step that you make is going to be 20 kilometers per second. If you use the optical definition, okay, channel 0 will have 21, channel 2 will have 21.2, so then that's why we use that. And these calculations that are here perhaps are not very clear, but it's just to calculate in which channel you expect the center of the galaxy to be, and then in which channel you start and in which channel you end. So this way, you can use the side channels to estimate the continuum. And that's what is going into UV-Cont soup. Basically, it's fitting the continuum with a first-order polynomial in the UVs, in the amplitudes, UV amplitudes. But then we can try to use, for the brave ones, we can try to make the image, and you can also do the continuum subtraction in the image plane. So, okay. Perhaps you can already go and do the plot MS. Yeah, everybody got the. You can go and try to plot, to start the imaging part, which is, yes, you can use plot MS to plot your amplitudes with respect to UV distance, and then you can see what's the largest baseline that you have, which, because you all know that the resolution, right, of your observation depends on the largest baseline you have, you can calculate how wide is going to be your point spread function. Remember? So this is the next section there, is to try to estimate the resolution of your observations, and then try to optimize the pixeling that you are going to, the number of pixels and the cell size. Because remember that this all goes into the fast Fourier transform algorithm. So a rule of thumb is when we know our beam size, we usually take like 3 or 4 pixels that cover that central resolution that we have. This is a rule of thumb to choose the cell size parameter. And then for the image size, we try to get 2 times the primary beam, the antenna primary beam. So in this case, yeah, it's a bit explained there how you get to these numbers. I can explain you.
I have this error when I use the code to...
Yeah, but don't use the so keep with the next steps, but don't use the continuum subtracted data set, but only use the .co87.
I don't know if it's
After he
something
subtracted,
useful.
he got that.
After?
After, yes.
After continuum.
See, yes.
But you are, what are you plotting here?
And then the amplitude with the channel. No.
With the scan.
No, but you are plotting channel number. This is the x-axis, and this is the y-axis.
Ah, the data.
So you are plotting you have 128 channels, so it's telling you the average.
Which is 64.
Starting with 0?
Yeah.
Yeah. So that's what if you change this to
63,
amplitude,
Yes.
if you change this to amplitude, then you should be able to plot.
Yep.
And then what average are you doing? Okay. And then you can even average per scan, but it's okay. Then we will see more.
No, because you're not subtracting again.
No, you are not subtracting anything. You are just plotting, but yeah, it takes a bit.
Thanks.
Yeah, so when it loads, I can. We didn't select points in the plot MS, right, with you guys? We can do that when it loads. Okay.
Mine keeps subtracting because I played it after we came back from the
Ah.
break. I forgot to.
But this is, I don't understand. So why, well, I guess the memory of them.
No, I can't do it.
Bueno, a lo mejor tú eres el único, you are the only one that...
I'm pretty lucky with computers.
because you didn't touch it.
Understand why.
Oh, you have here this one. Okay, perhaps it's not a good idea because you are contracting the subcontinuum on this very same. Are you also? Do you also have this plot MS here in your? Yes. Ah, okay, not exactly.
He hasn't changed the x-axis scan.
Yeah, it's okay. No, it's just to show you that if, for instance, I don't want to touch it because you are running the continuum subtraction, but let's say we want to identify this point there, right? You can also do it here, even if you don't change, because it will take, then you will have that one. So let's say I want to, this point is annoying. So how do I identify all these, like I want to get rid of all that, but I don't know where do they come from. So I select a region, I create a region, and then I select this point, and then I do locate.
That's the flagging, right? But without the commands.
Yes, that's correct. So this is the way you do it interactively.
Okay.
Because for random points like this, you might have like a couple of points.
What does to flag them mean?
Flag them. Flag them is raise a flag, which is telling the code, don't use this. Instead of, we are very conservative, we love our data so much that we don't delete it. We just flag it. So you have like a huge data set and perhaps you decide that a baseline is too noisy. So, okay, instead of deleting it, you could delete it completely. And we try to see, we process and we flag that part because we think it's not good. We flag it, and instead of deleting it, we just put an extra 0.1 byte that is telling the algorithm, don't use that point. Don't use that point. And then it puts like a red flag, or you can unflag as well. If after all you decide, okay, perhaps I was too strict, if you delete it, you can never get it back. If you just create an extra column with flag yes or no, you keep your data big all the time, but you can go back. And that's why you were saving this, here, you were saving this table in case you flag too much and you, I think you got the same. The same. Welcome. Okay. In case you do something wrong and you want to go back, this is a table, the flagging table, so it's where the zeros and ones are saved. You can restore the flagging table, the original one. And here, the interactive if you do it this way, you can flag more easily, like random points. In the command line, it's much better if you know you want to flag something for a long time or completely, because if I try to select the channel 63 because I don't like it from here, I might take also channel 64, so I can do it from the command.
Ones might be better.
Yeah. So in case, okay, I can delete my regions here. In case I want to know who are these guys, I do locate, and then in the log window, I get all the information of these points. So it's telling me which field I'm observing, which times, which baselines, and also the x and the y coordinates in this plot, because I'm plotting channel versus amplitude. So it's telling me this plot, these points have 0.5, 0.6, and they are located in x, blah, blah, blah. So in the case of that window that you had, the plot MS, perhaps it's closed already? Because it crashed. Okay. If you want, like here, like me, if I go and select those two guys here, what I get in the log message is that all the baselines are the same. They all correspond to baseline, the antenna 49 with PM04. So I do locate, and all of them belong to this baseline. So I decide I could do two things, or flagging it manually from here, or go to the command line and flag it there. In this case, it's very easy to flag manually. But for the flagging the scan number 163, then you want to do it from the command line. That's this spike that we had, I don't know, whatever. Anyway, so yeah, this is what we are doing. But you could flag it here if you like it. This data set is very good, so it's not a good example for freely flagging bad data. So we might take a look to some very nasty examples in which you have like a couple of 3 or 4 points that have like very high amplitudes, and then in your image you have some ripples there. But this one it was good for imaging. So tell me.
So that's why and I took a
yes.
screenshot.
Oh, this is a screenshot? No, but this is a plot MS.
Yeah.